All right, here's the lesson that we had last week on geometric mean. Oops. And this is going to be a super quick version. It's mainly for people that were absent to try and get caught up. We learned what geometric mean is, and so this is a geometric sequence, different than what you probably are familiar with as an arithmetic sequence. Geometric sequences change based on their being multiplied to get from one number to the next rather than added. So 8 times 2 is 16. 16 times 2 is 32. And then mean just means average, right? When we take the average of something, we're taking its mean. So if I wanted to take the geometric mean, that means the average in a geometric sequence. We're only worried about taking the average between two numbers. So the average, say the geometric mean between 4 and 16. The way I get that is I multiply the numbers. 4 times 16. That is 64. And then take that number's square root. So the square root of 64 is 8. And you can see that is the number that is the average between 4 and 16 in regards to being a geometric mean. Now the way we're going to use that in solving for we're going to be solving right triangles and thinking back to what we did with similar triangles and make a connection here. So we'll continue on and get there in a minute. So let's look for more on geometric mean. I'm going to kind of skip through all this verbiage. Here's one. They don't always come out clean and simple. So the geometric mean between 3 and 8. I'm going to multiply 3 times 8. 8 times 3 is 24. Take the square root of 24. Well, that's not a perfect square. So either one of two things will happen. If it's not a perfect square, I'll just enter in my calculator. Let's see if I can do it in this one. 24 and then square root. So it's a decimal 4.89 and however you might want to round that. But if I need to leave it as a simplified radical, I'm going to need to take this number and find its factors. And I'm going to think about what multiplies to make 24. Well, you shouldn't have to search too hard because you just multiplied these two numbers to make 24. So you can always start with that. 8 times 3 is 24. Then 4 times 2 is 8 and times 3. Now, when I'm looking for to simplify a radical, I'm going to look at when I find a perfect square under the radical, that can come out. So think of this as the square root of 4 times the square root of 2 times the square root of 3. You can separate all of them. So square root of 4 is 2. And then 2 and 3 don't have any matches, so they need to stay under the radical. So 2 times 3 is 6. So the simplified version of square root of 24 would be 2 square root of 6. Okay? So it just depends on the directions that you're given as to whether or not you leave it as a simplified radical or if you can use a decimal. Okay, that was some examples we did in class. Now, sometimes the problem looks like this. They give you the geometric mean. So 12 is the geometric mean of 16 and x. So let's go back to one way to set up a geometric mean is that the geometric mean is always going to be listed at the bottom of the radical, not the radical, the fraction and the top. They're going to always be across from each other. So the geometric mean you're going to always have twice. And then the other two numbers that you're finding the average of go in the other two places. Okay, so in this case, I would multiply 16 times x, and that equals 12 times 12, which is 144. And then to solve this, I divide by 16. X equals 144 divided by 16, which off the top of my head, I don't know. So I'm going to do 144 divided by 16, and that equals 9. Okay. So, and I think I might have missed this. I thought I got to this earlier before, but when we set up the geometric mean, we're going to always have the geometric mean will always be placed the bottom and then the top. And then the other two numbers will go in these two places. Okay, so that's how we're going to always set it up. And if you think about when I go to solve that, I are going to basically be multiplying these numbers and then taking their square root to solve it. So we'll get into more examples there. Okay. Here's another quick example. 10 is a geometric mean, so that is going to go bottom and top. A 4 and some other number. So to solve that, I have 4x equals 10 times 10 is 100. Divide by 4, and then x equals 25. Okay. So here's where we kind of put it together as to what we'll be using it for. So when we have a triangle, oh, I still got my page of notes here. I'll just maybe leave it up. If I have this situation, I have a right triangle, and then I've got an altitude that's been drawn. So here's the altitude. Okay, this is the altitude. It goes from the corner, and then it makes a right angle with the hypotenuse. So this, what we're talking about, only applies to this situation, a right triangle with an altitude drawn on it. And what I want you to see is that this is actually 3 triangles. You've got the very big triangle, which I've got in yellow. You've got the green triangle, which is the medium size, and you've got the little triangle, which is the blue one. And if we take this apart and look at the sides, I'll see that I've only been given the hypotenuse of the yellow triangle. It's 27 and 9, but you add that, so the entire hypotenuse would be 36. For the green triangle, I've rotated that around this way, and now its right angle is in the bottom left corner. So its legs would be 27, and x is what you've been given there. And then the blue one's facing the way it is the same way, so a leg and x. All right, so if I go back to what I know about similar triangles, let me erase all this and start over. I can make a similarity statement based on these corresponding parts. So I can say that the long side is to the long side, as the short side is to the short side. And either way I work it out, it would come out the same. If I said the green to the green is equal to the blue to the blue. You see, you get the same thing either way. Okay, so using similar triangles, we set up a proportion. And let's look at what happens when we solve this. I say x times x is x squared. 27 times 9. Get a calculator on the side. 27 times 9 is 243. Okay. And then to solve x squared, anything to undo something that's been squared, I take its square root. So the square root of x squared is just going to be x. So I'm going to take in the square root of both sides. We're undoing that it's x squared, and that becomes x equals the square root of 243. Okay, so think about what happened here. We multiplied 27 and 9, and then we took its square root. So that's why we can call this the geometric mean. We say x is the geometric mean between the two parts of the hypotenuse, 27 and 9. And whenever you have this triangle situation, that will always be the case. So we're not going to take the time to split up the triangles and build a similarity statement every time. We're just going to realize that x is the geometric mean between the two parts of the hypotenuse, 27 and 9. The altitude is the geometric mean between 27 and 9. And we can, I'm still going to write this proportion out just to make sure I get everything straight. Then I'm going to multiply and take the square root. Now, 243 is, well, let's check it out. I'm going to just, I don't know off the top of my head if that is a perfect square. It doesn't sound like it would be. 243 per n is 15.58. So we want to simplify this. Now I want to think about what numbers multiply to make 243. It's a big number, but I don't have to think too hard because I've already done it up top. I got there because of 27 and 9. So I know that 9 is a perfect square. It's 3 times 3. And this is 9 times 3. And that's another 3 times 3. Once I get a perfect square, I know that's going to come out of the radical as its square root. So 9 comes out as 3. So pairs come out as their number. Pairs come out as their number. So I got 2 3s coming out, 2 sets of 3s, and then 1 3 that stays inside. It doesn't have a pair. So 3 times 3 is 9. Square root of 3. So the final answer here would be that the altitude is 9 square roots of 3. 9 square root of 3 is a geometric mean between 27 and 9. Okay. Here's another one. I'm not going to take time to rewrite it. So we said x is the geometric mean between 5 and 10. Geometric mean goes bottom and top. 5 and 10, the other two numbers go in the other two places. Multiply, take their square root, and then I realized that that is 25 times 2. Square root of 25 is 5, and square root of 2 stays inside. Okay. So that's only one of the types of thing in this picture that's a geometric mean. There's 2 other geometric means, and that's when you have the legs. They work just the same. So let's go on to another picture. Here's some examples of, you may not be given the parts, you might have to calculate the parts. We talked about that real quickly. There's an example where it was the 8 is still the geometric mean. X is not always the geometric mean. It is the altitude, this part right here, that's always the geometric mean. So that goes bottom and top. Okay, not X. Don't just automatically put X as the geometric mean. It's the altitude that's the geometric mean. Okay, so let's go on to some different examples. Here we go. All right, so here in this picture, now the Y and Z are also geometric means. Okay, so we already talked about X, that's the yellow one. X is the geometric mean between 5 and 10. So the middle one, the altitude, is the geometric mean between the parts, the individual parts of the hypotenuse. But Y and Z, the legs, are the geometric mean between the side that they're with and the entire side and the entire hypotenuse. So for example, Z is the geometric mean, so that goes here and here. And then it's the geometric mean between 5 and the entire hypotenuse. So we got to add those numbers together, 10 and 15, 10 and 5 to make 15. So that's the proportion I would set up if I'm dealing with a leg. Okay, not the altitude. Y works the same way. It is the geometric mean between the side of the hypotenuse that it's with, the chunk, and then the entire hypotenuse. And we would find this out if we took the time to take these triangles apart and write similarity statements. You would get this similarity statement when you do that. I put out on Canvas another video to watch that goes into more detail about the similar triangles and splitting them up. So if you want to watch that, I posted that to our Canvas. Okay. Let me see if we can do one more. Here's one more example of a leg. Okay, we don't even have the altitude, so we're just dealing with this geometric mean. So I'm going to put it twice. And it's the geometric mean between 9, the side it's with, and the entire hypotenuse. So I need to add these up and get 9 plus x. So to work that out, I would do 9 times 9 plus x equals 15 squared. Let's see what that is. 15 squared is 225. Okay, then I'm going to distribute this. 81 plus 9x equals 225. And then just keep working it out. 9x. Subtract 81 from 225. So that would be 6144. Okay. And divide that by 9. X equals 144 divided by 9. Let's see what that is. 144 divided by 9 is 16. Okay, so that's how we're working these problems. And that's pretty much all we covered for geometric mean. And there's a worksheet on Canvas that you would want to do and practice. All right, talk to you later. Bye. And just a quick note, I just rewatched the video, and there was a lot of times when I said similarity statement, when I meant to be saying proportion. A similarity statement shows how two triangles are similar. So like if you had triangle, let's see if I can write here, A, B, C, and triangle D, E, F. So the similarity statement says that A, B, C would be similar to D, E, F, right? That's a similarity statement. And I kept saying that. I meant to be saying the proportions that you would set up. So the proportion is this part when I compare the sides of the two triangles. So say I would say AB over AC is equal to DE over DF. That's a proportion, and just keep that in mind. Nothing's wrong. It's just my wording. I should have been saying when we want to set up a proportion, that's comparing the sides and building two ratios and setting them equal to each other. Similarity statement is when I state that two triangles are similar. Just wanted to clarify that so I don't confuse anybody.